Hi, I'm Teresa Johnson. I work at Google on the C++ compiler optimization team. And the work I'll be talking about today has been implemented in the LLVM compiler. And that was a collaboration with some of the people from the upstream LLVM compiler, namely Mehdi Amini, who was at Apple and recently moved to Tesla, as well as David Lee, who is also at Google. And I'll be talking about ThinLTO. And this is a new framework for scalable and incremental link time optimization. Before I get into what ThinLTO is, I'm going to take a step back and describe actually what link time optimization is, because not everyone may be familiar with it, and talk about why you might want to use LTO, but then what some of the issues were that caused us to have to design a new approach. And I'm hoping by the end of the talk that you will feel that ThinLTO is something that you can enable in your, hopefully your day-to-day development. Okay, so looking at just a traditional compilation. Normally you have a bunch of processes that each parse a C++ code translation unit and turn it into IR, which is the compiler's internal representation of that source code, and then feed it through a bunch of optimizations that operate on the IR, and then finally generate native code into .o files. And then after all those are done, you go ahead and link all of this native object code. The compiles here are completely independent, and so you can completely parallelize these processes. You can either do make-j with a high parallelism factor, or if you have a distributed build system like we do at Google, you can farm them all off to different remote build nodes. And so you can speed that up quite a bit with the parallelism. The limitation, of course, is that each compilation doesn't have any visibility into what is defined in other translation units. And so that kind of limits some of the optimizations. Link time optimization was designed to deal with that limitation. So for link time optimization in Clang, when you say -FLTO, what happens is that the compile step no longer, it still does the parsing and does some optimizations on IR, but you no longer do code generation. And so what is emitted into the object files is actually the compiler's internal representation, and it's serialized out in some kind of binary format. For LLVM, this is called bit code. And now when you pass off all of these .o files to the linker needs to have some way of invoking LLVM. And so if you use the gold linker, there's an LLVM gold plugin. If you're using LLD, which is Clang and the LLVM project's own linker, it includes LLVM. So what happens is these IR object files get passed off to LLVM, and what LLVM does is it merges all of the IR into this large monolithic unit that we call a module. And just a quick note on nomenclature here. I talk a lot about, I mentioned modules. Unfortunately, this is a little bit confusing, and not C++ modules. In the compiler, we tend to refer to translation units as modules in their internal representation, just to be extra confusing. Okay, so now we have this large merged IR unit that has all of the IR for the entire application, and we can actually run that through the optimizer, perform inlining across it, finally do code generation and generate this large native object that's passed off to the linker, which then generates your application binary. And this happens completely transparently to the user. It's all under the covers, essentially. So you do -FLTO, you get some .o files out, you pass them off to the linker, you get an application binary back. And we call this a monolithic LTO implementation because you have this large monolithic unit of IR. So why do this? Well, as you might have guessed, the number one reason is for performance. When you merge all of these IR units into one, you now can perform cross-module optimization. So things that were originally defined in different translation units, now you have full visibility. And the largest benefit comes from inlining. So inlining calls functions that were defined in one module, in one translation unit, into call sites that were originally in another one. Another benefit can be binary size. So, and this is one of the advantages of doing this as link time optimization, because the linker is invoking the compiler, and it passes in some linker information. And so the linker will tell the compiler what symbols need to be externally visible, what are exported. And anything that's not exported from the unit that's being compiled can be internalized. And once we've internalized it, now we're basically telling the compiler that you see all references to those symbols. And you can do some more aggressive things like dead strip away things that aren't actually referenced or auto hide symbols. And another thing you can do is, and here's some speed up results for some benchmarks with LTO. And the biggest performance improvement actually comes from single source benchmarks. So they're not getting cross-module optimization, but what they are getting is, again, linker supplied information that tells the compiler that you can internalize symbols that aren't exported, and now you can do much more aggressive analysis and optimization. You can do better alias analysis, you can do constant folding, you can do a whole bunch of things that you couldn't do without that information. All right, so an example with 2 source files, and the important thing here to note is that one of them has a file static variable I that's initialized to 0. There's a set of it to -1 in one of the functions, and then an if condition that checks the value. And when we compile this through normal O2, we are guaranteed that we're seeing all possible references to I because it's this file static, but we don't know whether foo2 is called or not. So when we perform LTO on those and we merge them, and again, when we merge them, we're merging the compiler's IR, but I'm showing that here with source code just because it's easier to look at. So pretend this is the compiler's IR that's all merged. The linker tells the compiler that main is the only exported symbol. So everything else can be internalized, and that's represented here by turning everything else into file static. And then what the compiler does is reachability analysis. It starts with the exported symbol main and then follows through the calls to see what is reached, and it finds out that lo and behold, foo2 is never actually called. So we can use that to dead strip away foo2, and with it, the write of -1 into I. And now that I is only 0, we can constant fold that test away, which removes the call, and we get rid of that is then the last call to that function. We remove it, and that causes some other cleanup. And eventually, we can perform some inlining and constant propagation into main, and main just looks like this. So, I mean, this is somewhat contrived for this example, but it's a good idea of what benefits you get from the combination of cross-module optimization and the linker supplied information. So that's great, but LTO has been around for a while now, and not really a lot of people use it, particularly in day-to-day development. So why is that? Well, the first thing is now we've taken those optimization pipelines, which were fully parallel, and we are running them, running the entire combined applications IR in serial through the optimization pipeline. And so we've removed a lot of parallelism, and it's slow. So I'm showing here some numbers for an LTO compilation of Clang, the Clang binary itself, compared to a non-LTO build, and it's around 4 times slower. And even worse for incremental builds. If you fix a typo in one source file, for a normal O2, you would just recompile that one file, relink, you're done, it takes a few seconds. In LTO, you recompile it to IR, but then you have to perform the whole merged IR optimization part of your compile again, and that's really, really slow. It also requires a lot of memory because you're keeping the entire program's IR in memory at once. This is expensive, and you can do some work to try to prune and make your internal representation more efficient. So that was done for LLVM a few releases ago. Doing an LTO compilation for Clang took around 43 gigs. And that was improved over time to, we got it down to 11 gigs. But you can see that the rate of improvement has kind of fallen off, because after you deal with all the low-hanging fruit, you're still left with the fact that you have the entire program's IR in memory at once. And Clang is actually not really that large. If you look at the Chromium binary, particularly if you turn on debugging, that blows up the size of the IR even more. And we couldn't compile it after, we killed it off after 3 hours and 50 gigs of memory. Okay, so what we really want is something that is parallel, incremental, and memory lean. And particularly in order to enable LTO for day-to-day development, you really need to have a solution that's designed around these 3 features. Okay, so ThinLTO. Oops, sorry. ThinLTO was something that we designed a few years ago at Google. We have, and I'll show an example later, but we have some really huge applications that we want to optimize really well. They're very performance sensitive, and they're much larger than even Chromium. So regular LTO is simply not feasible. And we had a prior approach called LiPo, or lightweight interprocedural optimization, that we had developed we used to use the GCC compiler. So this was on a branch of the GCC compiler. And that gave us some scalable cross-module optimization, but it had some limitations, namely, well, there were a couple. One was that it was built on top of profiling. And so our key performance customers do use profile feedback because it does give them a performance gain. So this wasn't a huge problem, but it really limited how widely we could deploy LiPo. And it also introduced some brittleness to the whole process. Additionally, we were combining modules at parse time, and this additionally had some limitations, and it also kind of limited the scalability because we were combining entire translation units at parse time. So we went back to the drawing board and tried to figure out how we could design a different approach that would address the issues we had with LiPo and not hit the limitations of LTO, and that's where ThinLTO came. And we ended up presenting this to the LLVM community a couple years ago, and Mehdi from Apple got really interested, and so we had this really great collaboration to implement this in LLVM. So for ThinLTO, what we want ideally for parallelism is to not only have fully parallel compile steps, but we also want those back-end compilations to remain parallel. In order to have effective incremental builds, we need something smaller than the entire application in IR to put in a build cache. So we'd ideally like the backends to operate still on a module at a time. And then in order to keep this memory lean, one of the insights we had is that each module really only needs to see a small part of the rest of the application. You really don't need to inline from across the entire application. You only need to inline a few functions here and there to get most of the benefit. So we really only want to perform profitable cross-module optimizations into each other module. So this looks great, but how do you actually coordinate all of this activity? And as I'll show in a few slides in some more detail, what we do is introduce a thin serial synchronization point between the front-end part of the compile and the back-end compiles. All right, so let's talk now about how actually this works. So for ThinLTO, when you do the compile step, like regular LTO, you're generating data files that have IR. So same, you parse the file, you do some initial optimizations, you generate IR. But what we do for ThinLTO is we additionally generate on the side a small summary of each module. So the summary describes all the global variables and all the functions defined in that module. It also includes some metadata about the functions like the number of instructions, and includes information about all the references made from each module to other global variables and other functions. And then, as I'll talk about later for incremental builds, we include a hash of the module's IR. So for example, if we have a module with this red summary, let's say it includes a function, it defines a function foo. And so we record that there's a function foo, we record the number of instructions and some other information. And we also record the fact that it calls a function bar. And we don't know where bar is defined, though, at this point. But it turns out bar is defined in the module with the blue summary. And so that module correspondingly has a summary with an entry for bar and its metadata. All right, so now when we pass these off to the linker, and it hands us off to LLVM, instead of parsing all of the IR and merging all of the IR, we simply load these summaries and just aggregate them. And this builds basically a huge index of the application, and we call this a combined index. And now, once we have basically merged all of these individual summaries, we now get a full call and reference graph for the entire application. So now we know that foo calls bar, and bar is defined in bar.o. And we're not parsing any IR in this stage. So, so now that we have this reference graph, we can actually perform interprocedural optimization on the reference graph and the call graph, and then do some analysis, and then record those results for each module. So we might decide, for example, bar is a small function, it's likely to be inlined, so we mark that we'd like to import that into foo.o, so that's available for inlining. So we record that, and I'll talk about some other optimizations we do that we record later. And this is a serial phase, but it's not operating on IR, so it's still really, really fast. For Clang, thin linking takes a couple of seconds. So now these analysis results are passed to the ThinLTO backends. And what we do is launch a separate thread for each module to be compiled through the ThinLTO backend. And they're passed, each thread is passed its analysis results for that module. So for example, for foo.o, we would see that we want to import bar from bar.o. So we go ahead and load bar.o and just parse out the functions that we want to import and only import those particular functions. And then they're marked specially so that once we get through inlining, we go ahead and drop them because we know we have a definition somewhere else. And this happens in parallel for every other module, which is fired off in a different thread, potentially in parallel. Depends on how many threads you have in your thread pool. But, and they're completely independent. And then each of these parallel backend phases generates a native object that's handed back to the linker, which then goes ahead and links them. And like regular LTO, this is all transparent to the user. It's all done behind the scenes. So for distributed builds, we have a distributed build system in Google. We don't want to have this running on a single machine. We don't want to use different threads for the backend. So now we have to split things apart into different processes. So for distributed builds, there's a mode in which you can have a separate thin link process. And then each of these ThinLTO backends becomes a separate process that you can now send off individually to different remote build nodes. And in order to make that work, what we do is serialize out the analysis results for each module. And additionally, and I'll show how this works a little bit later with our build system, we also produce a small text listing for each module saying what other IR modules it's going to be importing from. And this is important so the build machine knows what other IR object files to package up and send off to the build machine. And so now you can fire off these backend jobs and send off the analysis results, all of the IR object files that it needs. And now the interprocedural analysis can go ahead and proceed in parallel in a completely distributed fashion. And each of these jobs generates a .o file with native code, native object, and that is fed to another job which does the actual final native link. All right, so now we have a solution that is it's faster and more memory lean, but we also want good incremental builds. And I mentioned earlier that the summaries each include a hash of the LLVM, or the IR module. Okay, so what we can do with that is that when we generate the analysis results for each module, we basically include the hash of that module as well as the hash of any module it imports from. So now each of these analysis results encapsulates the hashes of any module that affects it and all of the analysis results that affect it. And it encapsulates essentially all the information you need to make an incremental build decision about that particular LTO backend. And what we can do with that is you hash the input to the LTO backend, query a cache with it, and if there's a match, then the cached native object is returned and you never end up having to launch this LTO backend job. Okay, so for Google, we have a build system called Bazel. It's been open sourced. And the way Bazel works, in our build system, all dependencies have to be fully specified. So when you launch a Bazel build, the first thing it does is to walk through the dependency graph, and it builds something called an action graph for the build. So the action graph for a ThinLTO compilation would look something like this. So the brown boxes are all actions, and they're connected by connecting the outputs of each to the inputs to other actions. So you have, for a ThinLTO build, you'd have some C++ compile actions that generate these IR object files, an LTO indexing job, which is our name for the thin link, and then LTO backend jobs, which is the name we have in Bazel for the ThinLTO backends, and then finally a native C++ link. And so what we do then, once this is built, then Bazel goes ahead and walks through the action graph and sends off each action to, when its inputs are ready, to a different, potentially different remote build machine. But you'll notice here that I have some dashed lines in the middle, connecting essentially all of the IR object files to every single LTO backend action. And the reason is that because we're building this action graph before we've actually done any compilation, we have no idea what IR object files each LTO backend wants to import from. So we have to, at least initially, we have to kind of conservatively connect all of them together. And then what we do is there's a mechanism so that once the LTO indexing job is complete and we have those imports files, we go ahead and use those to prune any unnecessary edges there, connecting inputs to the LTO backends. So we would go ahead and prune away, and let's say only the middle LTO backend job is importing, so everything else has its other input edges pruned. And this is really important because, again, for these really large applications, we don't want to package off every single IR object file and send it to every single LTO backend node. It just would overwhelm the machines. Another thing that's important about Bazel is that the build system was already caching based with a content-based caching scheme. So essentially, you check the cache with the hash of the input for each action, and this matches up perfectly with the way that we can do incremental builds with ThinLTO, where we're hashing the input to the LTO backend, which is the analysis results. So that just kind of falls out. Okay, so now talking about some different optimizations that we can do with ThinLTO. I mentioned this earlier, but just to formalize it, when you do a whole program optimization in ThinLTO mode, you divide it into two parts. So the first part, it operates only on the summaries and on that combined index that we generate at the ThinLink. It doesn't look at IR at all. So you have to have all the information you need in the summaries, and then the results are recorded in the index. And then the second part actually applies that to the IR, and that's done in the ThinLTO backends. And that has to be, you have to apply those in completely independent fashion for each LTO backend. And so the example I had given earlier was importing. So for importing, when we're at the ThinLink, we go ahead and walk that call graph. We look at the number of instructions. We have some heuristics to guess what is likely to be inlined, and we mark things for import. And then when you get to the back end, it looks at the import list and it actually goes ahead and loads and links in the imported functions. There's some other examples that I'll talk about. Some are for performance, and some are actually for compile time. So the first example that I'm going to talk about is actually for compile time. And this is we call weak linkage resolution. And so in this case, I have two source files, and they're both calling vector pushback on an integer, which is a templated function. And template functions have what we call vague linkage. Like essentially they don't live in any particular, any one place. And so you have to instantiate the template function in any translation unit that calls it. And there's a special case of when you explicitly or specialize it, but assuming that you haven't done that, you generally have to instantiate that template function in every single source file that calls it. And I'm showing just a snippet of the LLVM IR for that, for vector pushback on an int, but it's not small. So you have to synthesize this in every file that invokes vector pushback on an int. And there's a lot of redundancy. And these functions are marked with a special linkage type that basically tells the linker that it's okay that there's multiple copies, that it doesn't violate the one definition rule, and the linker just picks one and throws away the rest. So with regular O2, you end up, like I said, with a bunch of redundant compilation. You have copies in every place that calls this, and you have to compile it and potentially co-generate it in all those places, and the linker picks one. With Monolithic LTO, this is handled really well. When you merge all the IR, you essentially end up merging them all or picking one at that point, and you naturally then only optimize and co-generate one copy. With ThinLTO, what we have to do is at the ThinLink time, we see that there's summaries from multiple modules for the same function, and we go ahead and use the information from the linker that tells us which copy the linker was going to pick. That's called the prevailing copy. And we mark that one to be kept. And we mark all the other copies so that they'll be dropped after inlining. And that's important because we want it to be available in the LTO backends for inlining. But once we're done with inlining, we know now that we have a copy somewhere else, and we can just go ahead and throw away the other copies. And this is pretty big. For Clang, for example, this one technique results in code generating 25% less functions. Another example of a whole program optimization we do in ThinLTO is dead global pruning. So if we have these two source file snippets, we have a global variable option, and then a getter and a setter. At the thin link time, we would have summaries for each of these, and we would have a reference graph that looks kind of like this. So we have reference edges from both the getter and the setter to the global variable. Now, if the linker tells us that only get global option is externally referenced, then what we do is we mark all those externally referenced functions as roots for some live variable analysis. We compute reachability, and then we can prune anything like set option, which we discover is never needed. We can prune it from the graph. And this has a couple of advantages. For one, you can do better optimization. Now, option, for example, is not referenced from any other module. So we can go ahead and internalize it. And that means that the compiler can then go ahead and constant fold it because it's guaranteed that there's no other writes from anywhere else to option. From a compile time standpoint, once we have marked a bunch of functions as dead, we don't go ahead, if they have calls, we don't bother trying to compute imports for them. There's no point because we know that we're going to go ahead and drop those functions. And they're marked so that essentially once you get into the LTO backend, they're marked as dead, and so you drop them at that point. All right, so on another subject, so profile feedback. I mentioned earlier that a lot of our peak customers use profile feedback to get good performance. Basically, with profile feedback, what happens is you either instrumented your binary or you use hardware sampling to collect information about what code is executed at runtime. And then you feed that back to the compiler so that it can make smarter decisions about how to optimize. Okay, so for ThinLTO, we don't want it to be, we don't want to require profile information, but we do want to be complementary. So we would like to do even better ThinLTO optimization when you have profile data available. Okay, so first, just talking through what you do with profile data, even in the absence of ThinLTO. So if we have this code and it has calls to functions hot and cold, and let's say hot is quite a bit larger than cold. If you don't have any profile data, the inliner tends to use heuristics like, I'd like to inline small functions. So it probably will go ahead and inline cold and maybe not hot. And obviously, the compiler doesn't know this because it doesn't have profile data, but this really isn't going to give you the best performance. And so when you do profile feedback, we are able to annotate calls with their hotness, and the inliner takes this into account. So it's going to much more aggressively go ahead and inline hot calls and not inline cold calls. And we really want to aggressively optimize the hot paths, and that's why we do this. Okay, so now if you split these into two different files, we need to, within LTO, we need to import those functions before we can even make them available for inlining. So without profile data, the thin link, the call graph looks like this. So we have a foo, and it calls both hot and cold, and we've recorded the number of instructions in these functions. So let's say hot is 3 times larger than cold. So without any profile data, the importing heuristics kind of mirror the inliner heuristics. So we're likely to think, okay, we'll probably inline small functions. So we'll probably go ahead and import cold and potentially inline it. And again, that's not going to give us the best performance win. So when we have profile data, the calls, again, in the IR are annotated with hotness, and we can record that in the summary. And then that gets propagated to the thin link call graph. And now we have edges in the call graph that are annotated with hotness. And we essentially, again, mirror the inlining heuristics and import calls more aggressively when they are hot and less when they're cold. Oops, what happened here? And the other aspect of this is, so that's a performance win, but there's also a compile time impact from profile data. It turns out for some of our large applications, 98% of them are cold. So maybe they're not executed at all, or they're only executed at startup time, which we don't tend to profile because it's not performance critical. But they're completely cold, and there's no point to inlining or importing them or inlining them. So by not importing them when they're cold, we can get a compile time improvement. Another type of profile-based optimization is indirect call promotion. So when you have an indirect call, like in this case, we have an indirect call bar. Without profile data, we have no idea where this might point. Let's assume that we're not able to statically analyze the targets the bar is assigned to. But with profile data, a lot of compilers like LLVM, GCC will actually, when you do profile collection, it will profile the hot targets for indirect calls. And so when you feed that back, we might see that bar tends to always call bar impl. And what the compiler does with this is it inserts a guarded direct call to that hot target. This not only gets rid of the indirect call when you take that path, but you also can now inline bar impl into the direct call. So that works, but unfortunately that only works when the target is in the same module. So if this is split into two paths, we need ThinLTO to help us get the indirect call promotion. Okay, so without profile data, in our thin link, we have two disconnected nodes, foo and bar impl, and we don't know that foo calls bar impl. But with profile data in the IR, what we can do is add that information to the summary. So we essentially see that there's a hot target here for this indirect call, so we kind of record that as a speculative direct call in the summary. And now in the thin link call graph, we have an edge between those, and we can simply go ahead and import bar impl as if it was directly called. And once you've imported it, now the backend can go ahead and actually do the indirect call promotion. All right. So now I'm going to switch gears and talk about how well ThinLTO performs. And the first set of numbers that I'm going to talk about, and a lot of the numbers I'm going to talk about actually are build time performance. And later we'll actually get into like how does the actual generated code perform. But starting out with build time comparisons, and here I'm going to compare mostly with GCC's LTO. And the reason is that GCC has a really well-tuned and really sophisticated LTO implementation. That implementation has two parts. It has a serial part called WPA, or whole program analysis, and that makes all of the decisions, the interprocedural analysis decisions, it makes all the inlining decisions, and then at the end, based on those decisions, it rewrites out partitioned IR. And each partition is then compiled by a different parallel backend process called an LTrans process. And that actually applies the inlining decisions and then does the rest of the optimization and code generation. So this is kind of nice because we can compare the serial phases of the two approaches and the parallel phases. And we looked at how these approaches performed for a few different applications. The first was Clang, the second was the Chromium open source browser, and the third was an internal application running in Google's data center called Ad Delivery. And I'm showing some statistics for these different applications, but really the important thing to focus on, and this is what determines how complex that interprocedural analysis is how large and dense the reference and call graph are. So if you look at, for example, Ad Delivery, the number of nodes, which is the number of functions in the program and the number of global variables in the functions, global variables in the application is more than 10 times larger than Clang. And the number of edges or the number of calls and references between those is more than 15 times the size of Clang. So that's really large. And so now first looking at just the serial steps. So let's compare the thin link to GCC's whole program analysis. And starting out with the peak memory. Okay, so for GCC, there's two sets of numbers. The reason is that GCC is operating, the whole program analysis is operating on IR. So whether or not you have debug info has an impact when you're operating on IR. For ThinLTO, there's no debug info in the summary, so the thin link is not affected by whether you're compiling with debugging on or off. So there's one set of number for ThinLTO. And as you can see, ThinLTO gets a bit bigger for the larger applications, but it's quite restrained in how much it grows. With GCC, it grows quite significantly, and particularly for ad delivery, even without debug info, we couldn't compile it. We ended up killing it off after more than 3 hours and around 25 gigs of memory. And so the time results look kind of similar. ThinLTO gets a little bit slower for ad delivery, but it's still under 2 minutes. And for GCC, because it's operating on IR, it simply takes a lot more time. Oh, and just as a note, as expected, LLVM's LTO, which is monolithic, also cannot compile ad delivery. Okay, so now looking at Chromium. Chromium is the largest of the 3 applications that all of these LTO techniques could actually successfully compile without debug info. And now we're going to look at both the serial phase and the parallel phase. So monolithic LTO is LLVM's LTO implementation. It's fully serial. So there's one set of number here. And as expected, it's kind of slow. It takes around 28 minutes to build Chromium. ThinLTO, I'm going to show numbers for increasing numbers of backend parallelism. And so the thin link, of course, is not affected by this. It remains the same. And as expected, the parallel time goes down as you increase the number of threads that you can run in parallel. For GCC, when you increase the number of threads, you're increasing the number of partitions that you're dividing the IR into. And so GCC is actually doing a pretty good job. It's much faster than LLVM's LTO. And the time does decrease as you increase the number of partitions. But as you increase the number of partitions, you increase the amount of cloning you need to do as you're rewriting out the partitioned IR. And this comes at an increasing cost in peak memory. So if you look at the peak memory for GCC, it goes up quite a bit as you increase the number of partitions. ThinLTO is not affected very much as you increase the number of threads. And the reason is that the unit of compilation does not change. You are still just compiling a module through the backend. Okay, so ad delivery could only be compiled with ThinLTO. So what we did for that instead was we looked at our distributed build system and we looked at how it scaled compared to just O2. And so we kind of ran some numbers constraining the number of remote nodes available for distributing the backend compilation and compared this. And you can see that ThinLTO is a little bit slower than O2. It does have a serial synchronization step in the middle, but it actually scales pretty close to O2, which was great. That was what we were hoping for. All right, now moving on to incremental builds and how that performs. So these numbers are building the Clang binary itself. So when you're doing a clean build, monolithic LTO takes a while. ThinLTO and non-LTO are faster. ThinLTO is a little bit slower than non-LTO, again, because you have that serial synchronization step in the middle. Now, if you touch a widely used header, so this affects a number of source files, and you rebuild, you have to redo a bunch of compile steps. And so it doesn't look all that much faster in any of the cases than a clean build. But really, the key is when you just make a change to an implementation file. So one.cc file. Monolithic LTO only does that one compile step and then has to redo the entire merged monolithic LTO optimization. For non-LTO, for O2, you only have to do one compile and just relink. So that's very fast. For ThinLTO, we redo the one compile, we redo the thin link, we have to look up in the cache for all the backends and probably redo one ThinLTO backend. And that happens in 16 seconds. So the thin link, like I said, is super fast. It's not operating on IR, so that can happen really quickly. Just a little bit more detail on how ThinLTO scales with increasing threads. And I showed some numbers earlier for Chromium, but this is going to have a little bit more detail. So first, this is now building the Clang binary. First, let's look at when there's no debug info, when we build Clang with no debug. Monolithic LTO is a bit large. It's around 5 gigs. If you build ThinLTO with one thread, which obviously is going to kind of serialize all the ThinLTO backends, but it's useful for seeing what the minimum peak memory is. That costs around 20 times less memory than monolithic LTO. As you increase the number of threads in your thread pool for the LTO backends, the peak memory increases a bit, but like we saw for Chromium, it doesn't increase all that much. It scales pretty well. Okay, now looking at building Clang with debug info. And debug info really greatly bloats out the IR. So for monolithic LTO, this is quite expensive. It gets pretty big. If you build ThinLTO with one thread, however, you only have one module's worth of debug info, and it's quite a bit smaller, 42 times less memory. Now, as you increase the number of threads, when you import functions, you have to import a bunch of debug info. And unfortunately, a lot of types are connected, so you end up having to, their debug info ends up, you end up importing a fair amount. And so it doesn't scale quite as well as without debug info. You'll see that it increases, the peak memory increases a bit more. But it's still significantly smaller than doing a monolithic LTO built with debug info. Okay, so now let's switch to runtime performance. So this is the performance of the binaries that are generated by LTO or by compilation. And so this is looking at all of the C and C++ applications in the benchmarks in the spec 2006 benchmark suite. And all of the numbers that I've run here are with profile feedback. So the baseline is going to be just normal O2, but with profile feedback. And then I'll have numbers for monolithic LTO. This is LLVM's monolithic LTO with profile data. And the blue bar is going to be ThinLTO. And so first looking at monolithic LTO. A lot of the spec benchmarks are not large, so they don't all benefit that greatly from LTO, but there's a range. And there's some that benefit, like Pavre and OmnetPP and Zlang BMK, which benefit quite a lot from LTO. So now if you look at ThinLTO, which is, remember, quite a bit more scalable, but doesn't have as rich of information to perform interprocedural analysis on, it turns out it actually does almost as well. There's a few cases where it's not doing as well, and that's where we know we have a few limitations right now. We don't do as aggressive whole program analysis for global variables. And so that's one of the things that we're improving. So we're missing that, and that's causing ThinLTO to be a little bit slower. But if you look at the geometric mean, it's actually extremely close. Current status for ThinLTO, we have support in 3 different linkers. So gold, LD64, and then the more recent addition is LLD, which is, this is Clang LLVM's own linker. And if you look at just the Clang documentation, it has a bunch of information about, where it's supported and also how to configure ThinLTO, how to turn on caching, and control the number of backend threads, et cetera. Okay, so the next thing I wanted to talk about is whether there's any implications for C++ development. Besides hopefully enabling you to use ThinLTO, does this affect the code that you write? And so there's one example that I wanted to go through here where I think there is an effect. So if you look at this case, we have a function f that's defined in foo.cc. It's called in a couple of different source files. Now, the current conventional wisdom says that if this is a small function, you might want to instead define that function in a header file, giving it the inline keyword. And there's an interesting note about the inline keyword, and I saw this mentioned in a talk yesterday. It's a bit of a misnomer. It doesn't actually tell the compiler to inline it. What it really does is give it a special linkage type so that the linker won't complain about multiple definitions. And so when you get to the link step, it knows that they're all equivalent, and it will pick one. But anyway, it's called the inline keyword, and you put it on the function when you move it into the header. And now what happens is, after parsing, you end up, after preprocessing, you end up with a copy in every single call site, and now the compiler can inline it when it decides that it's profitable. And if it's small, the compiler is likely to inline it. The disadvantage of this is that any translation unit that includes that header now has to compile a copy of F, whether or not it includes a call to F. And now the compiler is smart enough that it will eventually see that there's no calls to F, and it has a linkage type that means, essentially it gives it vague linkage, meaning it doesn't have to keep that copy if there's no calls to it. So it'll go ahead and drop it eventually, but you're still paying some cost for actually going ahead and translating it to IR and doing some optimization. And if there's any calls left to it, it has to keep a copy. So with ThinLTO, actually, you can go back to leaving it in your source file. And what happens is then we compile one copy to IR, we code gen one copy, and wherever we think we need it, you can simply import it. And those, like I mentioned before, those imported copies are marked so that they're dropped immediately after inlining. So we can import that where it's needed, potentially inline it, drop it, and it should end up being much more efficient. There's a couple caveats to this. Oops, showing it inlined. So a couple caveats. One, actually I'm going to go out of order here, is if you have the inline keyword in it, it has to be in the header. So if you put it back in the source file, just remove the inline keyword. The bigger exception to this is template functions. And I talked about this a little bit earlier when we were going through the example with vector pushback on an int. It has vague linkage, and so it has to be instantiated anywhere that there's a call site, unless you explicitly specialize it. But if you don't do that, you do need to leave the template function in a header. Otherwise, you get undefined references at link time, potentially. All right, some future work. So when we were talking about the runtime results, I mentioned that there's a few places where we're missing global variable optimizations. And so we're doing some work right now to extend the optimizations, the information in the summaries, basically, for global variables, and extend the types of optimizations that we can do during that interprocedural analysis. So this first example actually applies to functions, propagating function properties, but the second one is a little bit more geared towards this global variable issue. So some mod ref information, constant ranges, allowing us to do more interprocedural constant propagation across different modules. Another thing we want to do is where there are single call sites to functions, we'd like to just move that function over rather than import a copy. And the advantage here is that if you only have one copy, you can internalize it. And this, again, like I mentioned earlier, internalization typically leads to more efficient code generation and better optimization. And then the other thing that we need to do, and this is also an implication for C++ developers, is that right now, ThinLTO is not very well integrated with make. So if you say make-j and give it a parallelism factor, it's going to fire off a bunch of jobs. And if you're compiling a bunch of application targets, it will launch a bunch of links, LTO links, in parallel, not realizing that ThinLTO is going to spin off a whole bunch of threads in parallel. So if you're not careful, if you give make-a high parallelism factor, you're building a bunch of linking a bunch of applications at the same time on your machine, and they each fire off a whole bunch of ThinLTO threads, you can overwhelm your machine. So you have to be a little bit careful right now. But one thing we'd like to do is actually allow make-j to control the ThinLTO backend parallelism so that you don't run into trouble there. And so what I hope that you've gotten out of this talk is that you've seen that ThinLTO scales like a regular non-LTO build, but at the same time gets you the same or very similar performance benefits to a full monolithic build, a monolithic LTO build. And incremental builds, which are so critical for day-to-day development, are actually very effective with ThinLTO. So I'm hopeful that we're on the path to enabling LTO via ThinLTO by default in production builds and as well in your day-to-day builds. And that's all I had. So. Any questions? Yeah.
I want to ask about the profile.
Oh, sorry.
Wanted to ask about the profile-guided optimization. Mm-hmm. I work on a really large CAD applications that customers buy.
Okay.
I don't know exactly what they're going to do with that application.
Right.
You know, with your benchmarks, you run it through and you get a certain profile characteristic.
Right. I
could characterize one workflow. Could it actually do some harm if I use that data? Have you ever seen that? I've never tried it.
Yeah, I mean, certainly you want your profile data to be as reflective of how people are going to use your application as possible. So, you know, it's hard, especially if you're, I mean, at Google, we can kind of cheat because all my users are internal, so I can kind of piggyback off their load testing framework and collect profiles there. But it's a little bit harder. Now, one approach that we do have for, and we use this internally in Google as well, but we've also used it for collecting customer profiles, is hardware PMU-based profiles. And there's a technique called auto FDO, and basically the profiles can be collected with hardware profiles, and if you can get those from customer runs, then you can synthesize profiles out of those. So I guess I don't know if I have a great answer.
If I use a run from one customer, a different customer could use my application because there's a lot of functionality here. Could use it in a very different way, and it could actually hurt them.
It could. So yeah, I mean, I guess the best advice I'd have is to try and get as many, customer sample inputs as possible to guide that. Or, it's hard. I mean, you really do need a representative input.
So do you guys do it on stuff that we run?
On stuff that you run. The applications that I run are all running in Google data centers. So you're not really running them directly.
Yeah.
Yeah.
Okay.
So, yeah.
Thank you.
Hi there. I was just wondering, in the absence of profile-guided optimization, is there any provision for using, I'm thinking for things like virtual calls. GCC has a quite good speculative devirtualization setup. And I noticed that there was no information that was being captured about types in the ThinLTO.
Yes. And we are working on that. And that actually has started. So someone in Google has been working on augmenting the summaries with type information for two reasons. One is whole program devirtualization, so that's in the works, and it's partially where he works on Chrome, and so that is in the works, and having that optimization we know is important. And the other thing that they're doing that for is CFI, which is control flow integrity. So there's a lot of concerns around security, and that's one of the key security optimizations. And so that was implemented. Those were implemented with full LTO, and he has ported them to ThinLTO. And so I didn't talk about them here. That used to be in my future work section, but it's mostly there. So so that's definitely something that we have partially, it's already upstreamed for the most part. And I don't know that it's not on by default, and then I need to check on the status, but it's coming. Yeah.
Thank you.
Hello. So even though the static initialization order fiasco does not affect Google.
Say that again? Sorry.
Even though the static initialization order fiasco does not affect Google, because using statics that are non-global, non-plain old data is banned. Have you considered using the global reference graph as a means to solve a legal order of initialization for globals?
Oh, okay. I see. So the question's about global initialization order. Yeah. I haven't thought about that before. So in terms of using the graph to decide what actually from different modules could be what order they should be initialized. Yeah. That's a good question. Yeah, I had not thought about that. But
it doesn't have much value for Google because it's not a legal use of the language, but it will be very useful for other users.
Yeah, definitely. No, that's interesting. I hadn't thought about it, but I think that there's a lot of opportunity for putting things in the summary and then using that. You essentially have a picture of the whole application. And so as long as you have whatever you need in the summary and you can operate on this full graph and then record the results for use in the backend, then I think that there's a lot of, because there you have the whole picture and you could potentially come up with an initialization order and
or find out whether there is known that is possible.
Yeah.
Report as an error.
Yeah.
Okay. Thank you.
Thanks.
Great talk.
Thank you.
Very clear. It's awesome. One thing I saw, though, is one of your examples actually got worse in performance, where nearly everything got better. Why was that?
Was this, now are you talking about spec?
Yeah, it was a spec, so.
Let me go back.
It was like Hammer or something.
Hammer, yeah. That's a good question. Whoops, where's?
Yeah,
darn it.
One forward, I think. Yeah, you got to go through a bunch of stuff. I guess.
Yeah, let's see if I can do this quickly.
Yeah, click.
Okay. Oops, there. Come on.
Keep going. Go.
There. I don't want to do too fast and overshoot. Okay, here we go.
Oh, there.
There we go.
Yeah.
Okay, so Hummer, let me look here so I can see better. Yeah. So Hummer actually, I'm trying to remember what happened in Hummer. We looked at it, and I don't recall why it degrades so much with LTO. The good news is we degrade less with an LTO. So it's a win.
Well, yeah, that's what I mean. I saw for both of them, I was just like, that just made no sense to me. It seems like a very odd thing, especially because you have profiling guided information.
Yeah, I'm
so
trying to
you even knew what the test did.
What happened with Hummer?
Maybe.
I mean, you can always shoot yourself in the foot by doing things to. It's possible like we inline too much and the register allocation blew up or something like that with LTO.
Okay.
So, yeah.
Hammer is extremely cache sensitive, so
okay.
any movement there
Yeah.
can give you plus or minus 10%. It's
Okay.
noise.
Yeah. Okay. Thank you, Kostya.
Thank you. Thank you very much. Great.
Thanks.
Question
Yeah.
about
sorry, over here.
comparing Monolithic and ThinLTO. Is it a strict superset, the optimization is done in Monolithic as compared to Thin? Or are there any things that are only done in ThinLTO?
Right now, pretty much it's Monolithic LTO is a superset. It's it would be hard for ThinLTO, I think, to do something more aggressive than LTO just because it naturally has less visibility. So I think it's really more about getting as much of Monolithic LTO as possible for much less cost.
I sort of had the impression that like ThinLTO was the hot new thing, and maybe people are just implementing over there and not bothering to port stuff into the,
thank you for mentioning that, because now I just actually did remember something. So there is one thing, and it's not so much an optimization that ThinLTO enables, but the fact that ThinLTO parallelizes the backends, we have been able to enable a much more aggressive optimization pipeline in the ThinLTO backends. Monolithic LTO, the optimization pipeline that happens in order to keep things reasonably scalable and reasonable time for some of the applications that get built with LTO today, that pipeline is shortened up a bit. So ThinLTO does enable just more overhead. More time budget.
more back-end phases are turned on?
Exactly.
Like that? Okay.
Yes. Yeah.
That's good to know.
So we get more budget. That's really where you get the better.
I have a great talk. Question.
Thank you.
I'm in a situation with a code base with a lot of generated code and a lot of generated global variables, and I'm curious if I switch to Monolithic LTO to ThinLTO, what are the issues with the global variables that maybe I could fix to avoid the issues? I'm just curious if.
Sorry. So if
by more details about what
the
global variable
variable
is not in the ThinLTO.
Okay. So global variables. So I wonder if it's in my backup slides. So there was that example I showed at the beginning of the talk to just show what LTO does, how it cleaned up. There was that global variable I, and we were able to completely clean up one of the writes. So if you look at that with ThinLTO, and I wonder if I have it's going to take me a while. I have a ton of backup stuff here. But, shoot, is this it? No, unfortunately, I don't know if I have it. But essentially, we can't quite clean it up that well with, I don't have it here. We can't clean it up that well with an LTO because you end up still having the variable I there. We don't know the fact that it has essentially that the -1 value was never written, and so that's one place where we'd like to record some information in the some mod ref information in the reference graph, and maybe some constant ranges. The fact that it's constant, and you can basically. The problem is that in that example, the guarded. Let me think. Trying to reconstruct it, but essentially, if you have some information about the values that those variables take on, especially if they only take on a few constant values, you can do a much more cleanup. Okay. And so that's one of the places that we know we have to do a little bit more work.
Thank you.
Only a very short question. I'm curious, which GCC version you killed? Which was it?
Which GCC version did we use here? I think it was, trying to remember what was at the time when we did the results last year. I think it was probably, were they on 5.0? I forget. It was a fairly recent version. Now, internally in Google, we use a little bit, we have a branch off of GCC. So that's legs a little bit. That's 4.9, I think, but yeah.
Okay, and the second question is it always available on ARM architectures as well?
So what was the last part?
On ARM architectures.
On ARM architectures.
Yes, does it work as well?
ThinLTO?
Yeah.
It should. I mean, there shouldn't be any architectural constraints. I mean, it obviously depends on what linkers you have available.
Because you're passing the instructions in the object file, so you have to know about the internal instruction set.
Well, that's all up to LLVM. So the code generation is just whatever LLVM stock code generation is. So it supports ARM, and so it should generate, when you get to the ThinLTO backends and you perform code generation at the end, it should be able to generate anything that LLVM itself can generate.
So I can't use a ThinLTO, for example, with GCC compiled object files? When I compile my CPP files with the GCC, I have the object files, and can I use your ThinLTO for that?
You're right, yes. So if you're using GCC to generate, so remember the .o files, when you do LTO, either regular or ThinLTO, the .o files actually have the compiler's internal representation in them, not native code. So it's not parsing, in the LTO backend, we're not parsing native code, we're parsing the internal representation from the compiler. That's different for GCC and LLVM. So GCC's LTO also does stream out into its .o files like a GCC's IR, and they're not compatible with LLVM. So you can't mix, the first part of your compile can't be GCC and then mix it with LLVM's LTO. It would have to be client all the way through.
So then you have to use a LLVM compiler as well, not the GCC. So I have to use a whole package for that.
Yeah. So if you want to do ThinLTO, you have to. Yeah, right. Because those .o files, which are the compiler's internal representation, are not compatible between the two. So you'd have to use client. Yeah.
Okay. Thanks.
Yeah.
Hey, fantastic talk. Really enjoyed it. The question. So we do use distcc and CCCache to speed up build system.
Okay.
So how will this work with our setup?
What was the first thing you used?
Distcc.
Oh, distcc. I don't know if I can answer that question very well, because I'm not an expert on that, unfortunately. I do know for ThinLTO, the caching that we enable is, so it has it's sort of its own ThinLTO cache, essentially, that you set up. And unfortunately, I'm not giving you a good answer because I just don't know enough about distcc, and we have like I said, we have a different build system inside Google, and I'm more familiar with that. So, yeah, sorry. Anything else? Okay, thank you.